All right, welcome. Today we're going to pull back the curtain on what is, seriously, one of chemistry's most dramatic events, the formation of an ionic bond. You can think of it like a story of motivation, a high-stakes transfer, and this incredibly powerful attraction that, well, it builds the very world around us.
Okay, so here's the plan. We're going to start with the why, this whole quest for stability. Then we'll witness the Heist itself, this great electron transfer. We'll break down how salt is made, look at the power of the ions that are created, see how they build themselves into crystals, and finally, check out the unique properties of this kind of bond. Let's get to it.
Right, first up, the quest for stability. Every great story starts with a motive, right? So before we get to the action, we've got to understand what's driving these atoms to react in the first place.
So why do atoms form bonds? Well, it turns out atoms are rarely loners. You just don't find them hanging out by themselves in nature. They're always interacting, and that's because they're all searching for one thing, one single goal above everything else. And that ultimate goal is stability. Yep, just like a character in a movie, every atom has this one primary motivation. They just want to be stable. They're trying to get to this low-energy state, kind of like those super chill, noble gases on the far right of the periodic table. You know, the ones that just don't react with anything.
And what's the magic number to get there? It's 8. That's it. Having 8 electrons in their outermost shell, what chemists call the valence shell, that is the atomic version of winning the lottery. It is the absolute key to a stable, peaceful existence.
Okay, so that brings us to the main event, the great electron transfer. So how does an unstable atom get to that magic number 8? Well, some atoms, they don't exactly play well with others. They don't share. Instead, they take. This is where we get a dramatic, full-on transfer of electrons. And this, right here, is what we call an ionic bond. It's a chemical bond formed when one or more electrons are completely transferred from one atom to another. I gotta stress this. This is not sharing. It's a complete giveaway. It's a heist, where one atom just permanently snags an electron from another one. So, who are the players in this little drama? Well, on one side, we've got the givers. These are the metals, the elements over on the left side of the periodic table. They tend to lose their outer electrons really easily. Then, you've got the takers. These are the nonmetals over on the right. And they have a really strong pull. They're desperate to gain electrons. All right, let's move on to our case study, making salt. Let's actually watch this whole heist play out in real time with something you definitely know, everyday table salt, or, sodium chloride.
Okay, so here's the setup. You've got unstable sodium, or Na. It has one extra electron it is just dying to get rid of. Then you have unstable chlorine, Cl, and it needs just one more electron to be happy. So the heist happens. Sodium transfers its electron over to chlorine, and boom, just like that, both atoms are now stable. But they're also charged. Now, what's really interesting here is that we can kind of predict when this is going to happen. Chemists have this thing called electronegativity. It's basically a measure of an atom's greed for electrons. And the rule of thumb is this. If the difference in that greed between two atoms is about 1.7 or more, it's not going to be a negotiation. The electron is just going to get stolen. The bond is for sure going to be ionic.
So moving on to the aftermath, the power of ions. Because you see, this heist has consequences. Yeah, the atoms are stable now, but they're not the same as they were before. They're not neutral anymore. They've become something totally new. They become ions. So what's an ion? Well, an ion is just what we call an atom after it's either lost or gained an electron. Its whole electrical balance is now different, so it's officially charged.
And this gives them new identities. The atom that loses the electron, in our case sodium, it becomes positively charged. We call that a cation. Think of the T in cation looking like a plus sign. Then the atom that gains the electron, chlorine, it becomes negatively charged. We call that an anion.
And here is the absolute key takeaway. You've heard it a million times, opposites attract. Well, that strong electrostatic force, that pull between the new positive ion and the new negative ion, that is the ionic bond. It's not a little string connecting them, it's this powerful, invisible force of attraction. Okay, next up, life in the crystal. Because these newly bonded ions, they don't just, float around as little pairs. Oh no, they assemble themselves into something way bigger, way more organized, and a whole lot stronger. See, they don't form individual little molecules. They build a fortress. It's called a crystal lattice. You just won't find a single molecule of NaCl floating around. Instead, millions, even billions of these sodium and chloride ions packed together in this superordered three-dimensional pattern. It's this really regular, repeating 3D pattern of ions. So in our salt crystal, each positive sodium ion is surrounded on all sides by 6 negative chlorine ions. And, you guessed it, each negative chlorine ion is surrounded by 6 positive sodium ions. This creates this incredible, super strong, and really stable structure. All right, let's talk about the bond's unique properties, because this whole structure perfectly explains the real-world properties of something like salt. So, what are the consequences of building this kind of crystal fortress? What can these bonds do? Well, the strength of that ionic bond explains pretty much everything. It's why ionic compounds are crystalline solids, it's why they have crazy high melting and boiling points, and it's why they're very hard but also kind of brittle. They're also interesting when it comes to conductivity and solubility. That powerful attraction just locks everything in place. Let's dig into that connectivity mystery. So, as a solid, the ions are totally locked in place. They can't move. And since electricity is just the flow of charge, if your charged particles can't move, you can't conduct electricity. Simple as that. But the second you melt it, or more easily, dissolve it in water, everything changes. The ions break free from that lattice. They become free and mobile. And now that they can move around, they can carry an electric current. It's like flipping a switch. And this structure also explains why they're so brittle. Think about it. First, you apply a force to the crystal, like hitting it with a tiny hammer. A whole layer of ions slides over just a little bit. But that's enough to make ions with the same charge line up. Positives next to positives, negatives next to negatives. And that creates this massive repulsion that just shatters the crystal. Pop! So, when you think about it, if this one type of bond can build something as common and essential as salt, what other atomic heists are out there, shaping the world all around us? From the minerals in our bones to the very rocks beneath our feet, this ionic bond is a fundamental force, and it all starts with one atom stealing an electron from another.